In our redox reactions, we can use a concept called oxidation states to work out whether something has been or a substance has been oxidized or lost electrons, or if it has been reduced or gained electrons. So oxidation states, sometimes called oxidation number, can show us the total number of electrons that have been removed or added to an element to get it to its present state. We don't work out the oxidation states by counting the number of electrons transferred. We need to learn a set of rules. So when we actually learn these rules, what we'll see is oxidation will be shown by an increase in oxidation state from when the substance goes from reactant to product. Whereas reduction will involve a decrease in the oxidation state or the number. So we will see numerically a decrease from when it is a reactant to when it is a product. It's much easier for us to see that in an example. So we'll come across that rule again. So when we're looking at oxidation state or numbers, there's our basic knowledge in terms of chemistry and why electrons are lost and gained, really. In covalent or ionic bonds, electrons are shared unevenly between elements which have different electronegativities. So we're already aware of that. Okay, so you can either have polar covalent substances where the electrons are shared unevenly between two substances that are still sharing electrons, or in ionic bonds where there is a total transfer of electrons from one substance to another. So that's our knowledge in order to understand, help us understand anyway, oxidation states. So the oxidation state or oxidation number is a number given to an atom or ion to indicate the number of electrons it has lost or gained, as we stated earlier. These are the rules. We need to know them. We need to be able to apply them. So rule number 1, elements have an oxidation state of 0. And that's basically it. So oxygen, gas in diatomic form, carbon in any form, diamond, graphite, or our Buckminster fullerenes, and magnesium all have an oxidation state of 0. So we're just giving an example to apply that rule. For monatomic ions, the oxidation state is simply the charge on the ion. So copper has an oxidation state in this particular instance of +2 or 2 positive, same thing. Chloride has an oxidation state of -1. Simple as that. So that's rule number 2. The sum of the oxidation states of all of the atoms in a neutral molecule or ionic compound, it will equal to 0. So for water, for example, the whole compound will have an oxidation state of 0. However, we've got to look at the different elements involved there because each element will have a different oxidation state to make up that 0. So what do we mean by that? If we keep moving, we'll go through rule 4 and then we'll jump to rule 5 in order to do these examples. So the sum of the oxidation states of all of the atoms in a polyatomic ion equals the charge on the ion. So sulfate, which we can see here, will be equal to SO4 or -2 is equal to -2. That will be its overall oxidation state. Like I said, each element within, though, will have a different oxidation state, or will see its oxidation state. So some elements in fixed oxidation states have fixed oxidation states in all of their compounds. So we need to know these ones. Group 1 metals, all +1. Group 2, +2. Combined oxygen, -2. There are a couple of exceptions. Combined hydrogen, +1. Okay, there's an exception there. But if we have a look at our examples, we're not talking about the exceptions to the rule. So if we look at hydrogen and oxygen, we can do this algebraically. If we know that, we'll start with oxygen. So 2 hydrogen plus 1 oxygen is equal to 0 because we know it has an oxidation overall of 0. 2 hydrogens plus 1 oxygen with an oxidation state, fixed oxidation state of -2 is equal to 0. If we move that across, 2 hydrogens is equal to 2 over 2 and hydrogen is equal to +1. Which actually fits exactly what we've just said as one of the fixed oxidation states. So oxygen in water is equal to -2, its oxidation state. Hydrogen both hydrogens have a positive 1 oxidation state. Likewise with the sulfate, if we have a look at this, there's 1 sulfur atom in the sulfate ion. There's 4 oxygen atoms in the sulfate ion. The whole thing is equal to -2 as an oxidation state. So we don't know sulfur, unlike oxygen, which has a fixed oxidation state. So sulfur plus 4 by -2 for each oxygen is equal to -2. So sulfur minus 8 is equal to -2. So therefore sulfur is equal to +6. So each oxygen is equal to -2 and the sulfur is equal to +6. So that's how we work out the oxidation states of particular compounds and elements within those compounds. If we look at another little rule to know, most electronegative elements, or the most electronegative element rather, is given the negative oxidation state. The less electronegative one is given the positive oxidation state. So let's see how that looks like in theory. What does that mean in terms of chlorine in various acids? So if we look at chlorine, it's present in hydrochloric, hypochlorous, chlorous, chloric, and perchloric acid. The difference being each time there's an additional oxygen. So what does that mean for chlorine? Well, the electronegativity, En, of chlorine is less than that of oxygen. So that's something to keep in mind here as we go through these couple of examples. So with the hydrochloric, it's hydrochloric plus, or hydrogen, sorry, plus chlorine is equal to 0. Hydrogen has a fixed oxidation state of 1, plus chlorine is equal to 0. Chlorine is equal to +1. Rather, whoopsies, it's equal to -1. My algebras are out there. So that's equal to -1. If we keep going, then we have hydrogen plus chlorine plus 1 oxygen is equal to 0. Well, we know hydrogen has a +1 oxidation state fixed, plus chlorine plus a -2 oxidation state for oxygen is equal to 0. In this particular instance, this is where we're going to have, so this will be -2, bring that over, that'll be +2. Bring the +1 over, that'll be -1. So chlorine is equal to +1. So that is actually the case. Notice that the chlorine oxidation state has changed from one substance to the other, one acid to the other. If we go again and we say hydrogen plus chlorine plus 2 oxygens this time is equal to 0. So +1 plus chlorine plus 2 by -2 is equal to +3. And we can see it's changing each and every time because oxygen is more electronegative than the chlorine and it will maintain its oxidation state of -2. So you guys work out the next 2 examples and we will have a look at the next example separate to that table together. Here it's asking to determine the chromium oxidation state in the dichromate ion, Cr2O7, with a charge of -2. So we know that the whole algebraic equation, 2 chromium plus 7 oxygens, will be equal to -2. We know that oxidation state of oxygen will be maintained at -2. So 2 chromiums minus 14 is equal to -2. 2 chromiums equal to 12. Each one will have an oxidation state of, oh, missed it, +6. And there we have it. There's a few examples there for you to use. I will upload another set of examples or another set of questions that I want you to have a go at, and we will continue for homework. We will continue at the beginning of next lesson in order to work out the answers there.